Hello, my name is Moysis Symeonides. I'm a PhD candidate at University of Cyprus, and today I will talk to you about an emulation framework for IoT fog and edge applications. So, starting from the IoT devices transform our real world into information system, and the vast amount of the IoT data is input for diverse use cases like smart farming, like industrial use cases with industrial IoTs, in healthcare with wearable devices, and in smart cities. Of course, the IoT devices do not have the proper processing power in order to generate useful insights from their data, so they offload the data to computing platforms like cloud computing, fog computing, or edge computing. So before continue, let me introduce a motivating example for intelligent transportation sector. And let us assume that a taxi company wants to analyze region-based data from its fleet. So for that reason, the company will create a microservice-based application that includes two services: a partial aggregator that aggregates the data for a subset of the taxi fleet and generates partial results and stores the result in an in-memory buffer, and the backend server that periodically requests the partial results and aggregates them in order to generate the overall aggregation. Finally, users can request the generated data via a dashboard. So about the infrastructure, the company would purchase MECs, multi-access edge compute nodes, and place them in different regions inside the city. And of course, we'll deploy the application. So the partial aggregators will be deployed on MECs, and the backend server will be deployed on cloud. And taxis will send their data to the nearest MEC, and if there is no reachable MEC, for instance at suburbs, the taxis will forward their data directly to cloud via mobile internet connections. So in this use case, we have many actors like fog operators, like IoT developers, performance evaluators that face multiple challenges in such complex environment. So starting from the plethora of the devices, so the wide range of the devices contribute also in heterogeneity of compute resources, but also in diverse capabilities, sizes, and prices. And moreover, a faulty decision at this stage may increase the cost and the time to market for the final product, because the operator needs to replace the fault devices with new ones with the proper capabilities. So even if we select the best device for our use case, the deployment of the devices in a geo-distributed environment is time-consuming, since the operator needs to go to a specific geolocation, set up the devices, install the software, configure the networks, and of course, if we try to scale this infrastructure, the efforts are increasing exponentially. Furthermore, since in such environment we have mobile nodes, the network OS of the mobile nodes are influenced by the positioning of the node and by the wireless connections, and of course by the obstacles at the physical environment. So developers, in order to evaluate their applications, need to perform multiple trials, even at the real field. So think about the use case that the developer would like to evaluate an application and needs to rerun the same route with the car in order to find the performance of his or her application. So except from the mobility patterns and the mobility issues, we have many other faults and uncertainties in such environment. Basically, in a geo-distributed environment, we have increased possibilities for node disconnection, node failures, link drops, degradation of network QoS, packet losses, and load fluctuations. However, it's extremely difficult to reproduce these events in a controllable manner. So at the end, the users cannot be sure if the required quality of their services is achieved, and if the reliability of the services also is achieved. And of course, we have to monitor the whole infrastructure. And since this infrastructure is a multi-layered infrastructure with physical components, um, uh, virtualized components, applications running on top of them, we need to extract monitoring metrics from all these layers. This contributes also in efforts in the deployment, and users need to deploy sophisticated monitoring tools in order to extract these metrics. So for all these difficulties, users seek solutions to model and analyze the behavior of applications without needing to create a real fog-intensive infrastructure in order to deploy their applications. So for that reason, users utilize either simulators or emulators. On the one hand, the simulators do not actually run an application, but the users need to introduce the utilization metrics of the application and describe the infrastructure, and the simulator will predict the performance of the deployed application without running it. So in a system in a system approach, this is error-prone and suboptimal. On the other hand, emulators runs an application and actually mimic the production environment that this application will run. So with emulators, we have more accurate results. However, fog emulators, even if provide resource and network heterogeneity, do not provide, for instance, ad hoc updates at the topology, 5G abstractions, mobility patterns, and scalability. In order to highlight the state-of-the-art fog computing emulation frameworks, I present you this table. So as you can see, all of the current fog emulators provides resource and network heterogeneity. However, only few provides ad hoc changes or mobility or 5G concepts, and of course only one provides multi-host scalability. So we propose Fogify, which of course provides all these features. And the Fogify is the fog computing emulation framework. Before continue with the framework, let me introduce an outline of the rest of my presentation. So first of all, I will present you the features of our framework. Then I will describe some key design decisions that we took at the design phase of our framework. After that, I will describe the system overview and the workflow of the framework. And then I will provide information about modeling abstractions for static fog modeling description and the runtime evaluation model of the Fogify. Then I will describe some interesting implementation details. And finally, about the evaluation, I will present you the accuracy evaluation, in which we compare real and emulated infrastructure and we compare the results, and the usability evaluation based on the previous mentioned taxi use case. And here we will highlight how easily a user can evaluate his or her application. And finally, I will conclude my presentation. So Fogify is an emulation framework that enables repeatable, measurable, and controllable modeling, deployment, and experimentation of IoT services under realistic environmental assumptions, faults, and uncertainties. The key features of the Fogify is the fog at 5G modeling abstractions, resource and network heterogeneity, controllable faults and alterations, Of course, Fogify provides the positioning and mobility, and our framework is scalable from a laptop to a cluster, and also provides some monitoring capabilities. Sorry. Yeah. Before continue, let me introduce some key design points of our framework. First of all, we can emulate applications that adopt multi-service design. With multi-service, we are talking about microservices applications, big data distributed engines, distributed machine learning frameworks, and generally every application that has more than 2 services. Then the application services should be containerized and especially Dockerized. We adopted Docker because it's the most well-known and most popular framework for containerization. My third point is that we do not actually emulate IoT data, but the users need to provide us services that reproduce IoT data sets. Then, of course, the application runs in real time in our emulation framework. And finally, the emulator takes care of saving static and dynamic performance for compute resources and network quality of service and virtual network functions. So about the system overview. So a typical workflow starts with the user editing a Docker Compose file. The Docker Compose file is specification for describing multi-service applications and multi-service containerized applications actually, and then extends the Docker Compose with Fogify's model. And as I said before, Fogify's model introduce fog resources, network connections, mobility, ad hoc alterations, so on and so forth. Then the user submits the description to the Fogify SDK, and the SDK propagates this description to the Fogify controller. The controller is responsible to validate the description, and if the description is valid, then translates the description into the underlying orchestration primitives and submits this primitive to the underlying orchestrator. The orchestrator is responsible to instantiate the emulated instances, to constrain their capabilities, and to observe their execution. In our prototype, we utilize Docker Swarm, which is a multi-host Docker orchestrator. Currently, we also can utilize the Docker Compose execution engine, and we are working right now with Kubernetes in order to encapsulate also Kubernetes to our framework. At the same time, the controller submits the network QoS to the Fogify agents. Located on every cluster node, Fogify agents are responsible to introduce network QoS to the emulated instances by utilizing low-level, basically kernel-level commands of Linux. And except from that, also emulation agents capture monitoring metrics from the emulated infrastructure. At runtime, users can submit actions and scenarios. I will tell about them later. And actions and scenarios update the topology at runtime. Finally, users can request at any time the monitoring metrics and can process these metrics via Jupyter notebooks, which are data science tools, and we integrate Fogify with Jupyter notebooks in order to provide out-of-the-box exploratory analytics. About fog modeling abstractions. So for our model, initially users need to describe the fog templates. Templates includes services, nodes, and networks. Services, as I said before, are inherited from the Docker Compose, so they need no alteration at their code bases or their configurations. Nodes actually are compute resources of a fog infrastructure, and users can describe uh, properties like processor, memory, and disk. And the networks are interconnected networks that the emulated device will be connected to them at their execution. So, for instance, we can apply uplink and downlink QoS like latency, data rate, error rate, etc. But of course, there are many there are many networks that are not so simple. For that reason, we introduce the 5G networks templates. And let us assume that the previous mentioned use case utilize a 5G network. So in a 5G network, we can have mid-haul connections, the connections among the MEC nodes. We can have backhaul connections and the QoS, which are the connections between the MEC nodes and the cloud. Also, we have wireless connections, but in these connections, we don't have static QoS. For that reason, users can introduce parameters for the base station, for the antennas actually, and for the mobile devices. And these parameters will be translated into the respective QoS based on the positioning of the mobile node. Then we have virtual network functions like firewall rules and traffic policies. And finally, in a such network, we need to provide also the geoposition of the antennas. So the geoposition of the antennas is a list of the latitude, longitude, and altitude points. Of course, with the fog templates, we don't have a fog topology. Somehow we need to combine them into a fog topology. For that reason, we introduce in our model, a fog topology is a set of blueprints. So for instance, here we have 10 blueprints at each topology, and a blueprint is a combination of a node, a service that will run on top of this node, a set of networks that the node will be connected to, a location, either geolocation or a virtual location like cloud, an optional replication factor, so the user can set the number of the similar devices that the emulation framework will create, and the label, which is the identifier of the emulated node. So right now we describe the static description of the fog emulation and the fog topology, and somehow we need to introduce runtime updates. For that reason, we introduce actions, and actions can change the topology at runtime. Specifically, we have failure actions, which destroy a failure action destroys an emulated node at runtime. Scaling actions, both horizontal and vertical, so we can increase the number of the devices or decrease the number of the devices, or we can increase or decrease the processing capabilities of a specific device. Network alterations, we can disconnect a node from a network, or we can ad hocly update the network characteristics of a specific emulated node. Stress actions that inject CPU and IO intensive workloads to specific emulated nodes. And positioning updates that the system transfer a mobile node to a new position and updates its connectivity with the respective to the respective position. Except from the static, except from the ad hoc introduction of actions, users can also introduce scenarios, and the scenario is a sequence of time-scheduled actions that the Fogify will execute to emulate more complex user-driven experiments. So For instance, here we have a trajectory, and the taxi one at the 5th second of the scenario execution will be transferred to a specific geolocation. Similarly, after 5 seconds, again, the taxi will transfer to a new geoposition. And finally, after again 5 seconds, the taxi will transfer again to a new geoposition. So in this way, we can describe either trajectories or a sequence of failures and topology updates. So some implementation details about our framework. So starting from the Fogify SDK, the Fogify SDK is a Python library that provides methods for topology deployment and the methods in order to users deploy actions and scenarios at runtime. Also can retrieve monitoring metrics from the underlying from a running emulation and can provide out-of-the-box exploratory analytics. Finally, provides functions in order to create, in order users to create programmatically the Fogify's model, so users can build on top of this Fogify SDK new abstractions or can create large-scale deployments. Of course, we have a monitoring system. The basic monitoring metrics of our monitoring system are the CPU utilization, memory utilization, network I/O, and disk I/O. And also, we provide a method that users can expose application-level metrics from their applications, and in this way, can compare both utilization metrics and application-level performance. So another point is how the Fogify translates the description into an execution environment. As I said at the beginning of my presentation, we utilize containers. And in order to isolate the different containers, of course, we utilize the Linux namespaces. And in order to constrain the resources of a container, we utilize cgroups. For some resources, the constraining is straightforward. For instance, if I have to emulate an edge node with 2 GB of RAM on top of a host with 12 GB of RAM, I can set 2 GB limit to the container that executes this service. However, for other resources, like CPU, the mapping is not so obvious. For instance, if I have to map an edge device with 2 cores at 1.4 GHz on top of a host with 12 cores at 2.4 GHz, it's not so obvious how can we emulate such device. For that reason, we create the CCR, the cumulative clock rate, which is the multiplication of the number of cores of a processor with the frequency of the processor. So we compute the emulated CCR, the CCR for the emulated node and the CCR for the host. And we found the rate between them, and we set this rate as the limit of the container, since the secret gives us only the ability to set a portion of the CPU as a limit of as the processing limit of a container. About the network QoS and virtual network function enforcement. First of all, for its network description, the system creates an overlay, a virtualized overlay mesh network by utilizing VXLAN, and connects the respective emulated node on it. And in order to apply the virtual network functions and QoS, utilize, for instance, for firewalls, the system utilizes IP tables and checked the rules in the network namespace of the emulated node. Then applies a packet level monitoring module in order to extract statistics about in the packet level, and then creates a tree-based structure that shapes the network QoS. We utilize the Linux TC2 in order to create this structure, and we apply the final rules at the leaves of this tree. Except from the simple, let's say simple enforcement of network QoS, we have also 5G networks. So for that reason, we created the 5G slicer plugin. And the plugin takes us into the Fogify model, the model that I described earlier, creates an in-memory conceptual graph. In this graph, the nodes are the devices, both network devices and compute devices. And the links between the nodes are annotated with the network QoS for specific link. And in order to create the network QoS for the mobile nodes to the network components, we apply some mathematical functions from network community. Finally, we translate the network conceptual graph via FogifySDK into an execution environment. About the evaluation, our evaluation is twofold. Firstly, we examine the performance differences between real and emulated infrastructures. And we have also an example of the scalability of the system. And then we evaluate the usability of the system by exploring the before mentioned real world taxi use case with multiple scenarios. So in our first experiment, we emulated 4 compute nodes, 2 VMs, one located in London, another VM located in Paris. And we have also a Raspberry Pi 3 connected to the local network via Ethernet, and a laptop connected again to the local network via Wi-Fi. We took metrics for every connection in this infrastructure, and we replicate the same infrastructure in our framework, and we take the same metrics. So according to the network QoS, Fogify does not only capture some outliers and has a small overhead at low latency connections. In the same infrastructure, we deployed a real application. Actually, we deployed an ML inference application, and this application is deployed to the cloud server. We had also a service that performed a pre-processing, and we deployed this service to the Raspberry. And we had also a workload generator. So the workload generator sends images either to the Raspberry or to the server. And we have 2 different experiments. So for one experiment, the workload generator sends directly to the server images. The other experiment is to the workload generator to send images to the Raspberry, and the Raspberry resizes the images and sends them to cloud again. So again, we emulated the same environment with Fogify emulation framework, and we observed the maximum deviation to be between 5 to 8% in some experiments. Next, for connectivity accuracy of 5G networks, we measure the data rate between the radio units, the antennas, to the mobile nodes for a real testbed from Patra's 5G testbed for different distances from 100 meters to 170 meters. And we captured the data rates for 2 different configurations of the radio units. So the radio unit, in one case, had a transmit power at 33 dBm, and at the other case had the transmit power to 23 dBm. As you can see, we have a percentage error less than 12% for 23 dBm and about 5% for 33 dBm. Furthermore, we observed a higher error at 125 meters. So we consider a reflection or an obstacle at the field measurements at this specific point. About the scalability of the system, we installed the emulator on top of 3 different sized clusters. The first cluster had 1 node, the second cluster had 2 nodes, and the third cluster had 3 nodes. We deployed the same application, but we doubled and tripled the service of the application. And we observed that the emulator proportionally extends its emulation capabilities based on the underlying resources with only a comparable raising of bootstrap time. And finally, the usability evaluation of the before mentioned use case. So for this experiment, we submit a scenario with multiple actions. For the first 2 minutes, the application runs properly. Then we introduce a network delay for 3 minutes. So as you can see, we have a decrease at network traffic at the beginning of this period, but then the workload generator starts again to send data through the regional network. After that, we return the system to normal. And as you can see, again, at the beginning of the period, we have a spike because the QT request starts to go to the local network rapidly. Then we introduce a very high network delay. So the car workload generator actually get timeouts at this network. So redirects the traffic through the mobile internet. For that reason, we can observe an increased cloud CPU utilization and some data to transfer through the car region 1 internet network. Then again, we return the system to normal. And finally, disconnect actually destroys the MEC node 1. And again, we have this similar effects as the increased network delay. So we can observe again an increased CPU utilization at cloud and an increased traffic at the car region 1 network. So in conclusion, with network alterations and fault injections, users can comprehensively evaluate the execution of their services under extreme conditions and can identify unpredictable outcomes of uncertainties to their service behavior. Except from this example, we have also other use cases in our paper. So first of all, we highlighted how up-level metrics help operators to evaluate their applications. We illustrate how node profiling is highly beneficial for capacity planning. And also, we had scenarios for mobility patterns, scaling actions, workload alterations, and how these actions influence the performance. So the Fogify created in the Rainbow Horizon 2020 project. So we are not the only lab that utilize Fogify for testing. So we have actually we have utilize Fogify for testing big data engines like Spark, Storm, etc. We have also partners that utilize Fogify in order to evaluate use cases like human-robot collaboration in an industrial IoT environment, and some works that utilize Fogify examine the service placement and task placement in a fog geo-distributed environment. Yeah. In conclusion, I present you an open source emulation framework for IoT edge and fog applications. So the framework provides a powerful modeling abstractions for fog and 5G deployments. Also, users can introduce faults, mobility patterns, and alterations to the running emulated environment. The framework implements realistically 5G concepts like slicing, MIMO, virtual network functions, and network monitoring. Also offers any scale experimentation from a laptop to a cluster, and provides monitoring capabilities. I provided some implementation details about, of course, about the modeling of the fog deployment, and also about the resource management and network shaping. Some thoughts about our future work is and we try to make this is the emulation of different CPU architectures and components like GPUs. And we try to emulate embedded sensors as data generators to our emulator. So thank you. The Fogify is open source. We have also a documentation site for both Fogify and 5G Slicer, which is the plugin of the 5G networking. We have some demos that we demonstrate the usability of the Fogify 5G Slicer. And also we have a video for my presentation from Symposium of Edge Computing of 2020. Thank you. Currently, we scale the emulation with tens of nodes. So, but actually, if you have resources, we can scale infinity, let's say. But yeah, currently, I test the framework for tens of nodes. So for 50, 60 nodes, can scale easily. This effort is being done in the framework of a new project, or it's independent? It's actually like complementary of an EU project. So it's independent, but it's utilized by a EU project at the end. Given the other, have you experimented with other visualization technologies apart from Docker? I mean, at least for the edge platforms, something like IoT, no, no. Currently, we use only containers. Yeah, okay. Since the Docker can utilize QEMU, we tested also QEMU, but you know, it does not change anything about the framework. Thank you very much for this very nice presentation. I'd like to add something from the fact of the wireless networks. I saw to mention the capacity Mm.
formula or survival. You also, or can you also consider the effect of interference?
We don't. Currently, we don't consider the effect of interference because we do not model. If you know, we are coming in from cloud computing. We don't know so much about the networking. For that reason, we do not model the interferences. But if we have the functions, we can model it easily.
I mean, is it possible to extend it?
Yeah, yeah, yeah. Currently, we do not go in this direction, but the framework is easily extensible for that direction.
Also, I have another question about that. You said that they can about the 5G, let's say, or let's say, somebody would like to test other IoT.
Yeah, you can. If you can model
or some other interfaces. Are there any available work?
Currently not, but if you can describe the wireless networking of a 5G network with specific parameters to our model, we can emulate this. But we don't have specific models for LoRa networks or other type of networks. Mostly we are working on MIMO channels. So, yeah.
I just also like to ask something about the edge application using when you use the make, let's say those, what sort of pre-processing do you make? Make some sort of support, let's say, communicate with the cloud the server, or is it something just to aggregate the data and send it over?
You are talking about the use case.
Yeah,
yeah, we just aggregate the data. It is a use case to highlight the framework. It's not, let's say, sophisticated use case of edge computing. So yeah, we capture the data from the taxis and we calculate a simple statistic, and the cloud periodically requests every MEC node and generate the statistics, the overall aggregated statistics at the end.
This is more or less the same logic that we use for the example of the Raspberry Pi.
Yeah, yeah, but yeah. But as I said before, we utilize Fogify for other applications as well, like big data engines. We deployed a Spark cluster on top of a geo-distributed deployment, or a Storm cluster, etc. So, yeah, I highlighted some very simple applications, but in Fogify you can emulate much more complex applications. The only requirement is to be containerized.
Well, this question links to what was asked before about interference and other error interfaces and such. I see that you have some sort of network modeling in your system, but of course you have everything there. For example, if you want to model interference, sophisticated sophisticated RRM or a customized slice TC that will be coming forward, then you would have to somehow simulate their effect and then enter the end product of such interactions into what you call their network mode. To do that, you would need a methodology and to a bit more about what goes into your network model. Have you thought about that any further?
Yeah, as I said before, yeah, we are talking about these issues, about interferences, about the antagonizing, let's say, bandwidth, etc. But currently, we do not have something more sophisticated than this. But yeah, we are open for collaborations. I mean, we are not mastering this field.
One question is, how customizable is it to your network modeling part? Can the user change things there? How easy is it to do that?
Look, if you are talking about the model, yeah, the users can change the number of antennas, can change the frequency carrier, the bandwidth, transmit and receive power, the path loss, etc. But if you would like to introduce new functions in order to generate the network QoS, then you need to program them. I mean, it's not just a configuration. You need to write code, but it's not difficult.
Yeah, I understand. Can you change the parameters that dynamically in the middle of a run?
Right now, not, but it is an interesting. It's very interesting direction. I mean, it is not so difficult that it's really interesting. I didn't thought about it.
Thank you.
I have to say that I'm not very familiar with it. I'm very interested in or like I said, more from the side of the maybe perhaps from the side of a couple of naive questions. One is how difficult it is to try to extend this to the 5G.
Actually, the 5G controller sits on top of the Fogify. So users need to extend either a 5G controller or can introduce a new controller for a different network. So it is not so difficult. I mean, so you do not need to re-engineering the underlying emulation. You need to build on top of it.
And there are no implications to the other components of Shopify.
Yeah.
There are no making assumptions that inhibit if you have to introduce some higher frequency.
No, I mean, no.
Another thing that I found interesting, but I think I understand is you certainly can change things while it runs, and you can have either ad hoc changes or you can have scenarios.
Yeah.
How, I mean, practically, how does one do this ad hoc change? How do you interact with the system?
Yeah, we have the FogifySDK, which is a Python library. So in this Python library, you can write something like Fogify.update network. You can introduce the emulated node ID and the characteristics of the network that you would like to be updated for the specific emulated node.
So that's like an interactive environment.
Yeah, we built a Python SDK in order to communicate with the Emulators API. So we have an API, but it's much more easier for users to write Python than just send JSON objects to a URL.
If you go to the backend, what does it take to create an emulator? What sort of maths or modeling goes into the different aspects?
The difficult part is to understand mostly how the virtualization technologies work? How can you emulate, how to enforce the network QoS, which is not trivial, and how to engineer the stuff? I mean, it's not so mathematical, at least the Fogify, because the 5G slicer has some mathematical functions from the networks, but the Fogify, it's not so mathematical, but it's more engineering, but has some tricky parts in the virtualization and the network virtualization, and how the virtualization of the network uh, will have the same effects as a physical network. This is a tricky part of the emulation.
And you find this, so this is what I call modeling network. You find this described in papers.
No. No, I found I found this by reading the whole documentation of the Linux tools. So I found how can I save the network, and I applied this knowledge. Um, Actually, I found how to save the network. I built the model and found how to translate the model into low-level commands. So that is the difficult part of the emulation implementation, the implementation of the emulator.
Any other questions? If not, thank you again.
Thank you.